what is it? What does it mean? Well, it's like some volume, right? So it's like you want to say, well, here is that ball of radius 1. Then you'll think about the graph of this function over that, which is, I don't know, I'm not very good at drawing these three-dimensional pictures, but that's like traces out the upper hemisphere. So in essence, we just want to work on that volume. And how did you do that in calculus theory? You probably like said, well, we'll break that domain up into a bunch of little chunks. And I don't know, that's probably as fine as I can draw. And then over each of those little rectangular pieces in the domain, you said, well, I'm going to estimate the area over that small little rectangle by figuring out what height it should be. And then drawing a little rectangular prism, and computing its volume. So what did you do? You said, well, over that point in the cube, that's how high it is. So now the picture's going to really go to crap. I draw that cube, which is supposed to be right on the boundary of that sphere. You'll compute its volume by knowing what the formula for the volume of a cube is. And then you'll add all those up. By taking more little pieces, you'll get a better estimate. And that's what you did in Calc 3. That's exactly what we'll do now to compute the volume. We'll think about taking the region we want to integrate over, breaking it up into a bunch of little pieces. Pieces which we know how to evaluate the volume of, the n, well, in this case, two-dimensional volume. And then we'll build little prisms over that. And we should be able to just state what the volume of those should be. That makes sense as a plan? Yeah, so let's do that. Let's define the Darboux integral. So we will only integrate over figures in this class. So let's let x be a figure. A subdivision of x is some finite collection of subsets of x such that for each element of that subset, that thing is a figure. I'll talk about breaking the domain up into figures. X is equal to the union of all of these sub-figures. And, well, any two different of these sub-pieces might intersect each other, but they intersect each other in something that has no volume. And let's just go ahead and check that that agrees with what you do in Calc 3. You draw this sphere, note this ball, there's B, and you break it up into these little pieces. Each of those pieces are like an intersection of a rectangle with a ball. Both of those are figures, so this is a figure. Each of those little pieces is a figure. And I don't know, there's one of them, there's I, there's J. Do those two squares intersect at all? Yeah, they share a side, right? But what's the area of a line segment in R2? 0? So this indeed satisfies all of those conditions. This just gives us even more freedom. I can break up this ball into any collection of subfigures. There's no reason to just take that decomposition. I could say, well, I'd rather integrate in, say, polar coordinates, in which case you would try to break it up into pieces that look like that. And each of those are figures. You can compute the area of each of them. And you can write down the corresponding sum. In fact, that's like an integral you would want to change into polar coordinates. depending on how well you remember your Calc 3 days.
Is that kind of how that like transfers over to this? Just kind of changes how you take it, how you kind of split up the figures?
Yeah, so there's this like the change of basis stuff.
Yeah.
So the change of basis matrix says, well, if you want to rewrite this in polar coordinates, you would like want to rewrite map a square onto that circle. So that one of the directions goes to radius, the other one goes to angle. Then somehow this change of basis formula is supposed to say, well, how much are each of those little squares distorted? So the area of this little square should somehow tell you what the area of that little square-ish piece is. And the change of basis formula tells you how. Or at least it does a good enough job of approximating it so that when you take a fine enough subdivision, the error goes away. Cool. So apparently then, so we're going to break up the region into a bunch of little pieces. And you know what I'm going to do next. If you want to estimate, well, yeah. Let's flip forward a little bit. If you want to, let's flip forward quite a bit. So where is the definition of, Chris, don't you even know how your notes are organized? S plus S minus. Ah, okay. Ah, there it is. Okay, so all the way up on page 5, there's a definition of integral. And it'll be defined in terms of an upper integral and a lower integral. And you probably already have a pretty good idea how those will be defined. Like the upper integral will be like an infimum of a bunch of upper bounds on the area, the volume under the curve. The lower integral will be the supremum of a bunch of underestimates. Let's get those over and underestimates first. Well, no, let's do this warm-up first. Okay, let's keep our stomach straight. So, here's one. Let's suppose you have a figure of x, and delta is a subdivision of x. If you add up the volume of all of the pieces in the subdivision, what should you get? The volume of the original thing? Right? If you've honestly broken this up into reasonable pieces and you add up the volume of the pieces, you should get the volume of the original. If you're not careful and you, so this will be another like tangent into weird counterexamples and analysis. If you're not careful about what shapes you allow, you can come up with a way of breaking the sphere up into 2 separate pieces, each of which has the full volume of the sphere. This is the Banach-Tarski paradox. And so what that tells you is you need to be careful about what shapes you allow. That's why we only study figures, because things can go sideways really quickly. So let's let x be a figure, and let's take any subdivision of x. We need to show that the sum of the volumes over the subdivision is the same as the volume of x. And, well, there's a good way to make progress. By assumption, x is the union of the volumes of the individual components. Do we have some proposition that tells us what the volume of a union is?
Yes.
Yeah, it's like compute the sum of the volumes, subtract the volumes of all the pairwise intersections, add the volumes of all the triple intersections, subtract the volumes of all the quadruple intersections, and so on. And when you just make sense of that formula, it looks complicated, but it's not that bad. It's the sum from I equals 1 to n, where I is how many sets you're going to intersect, of -1 to the I plus 1, because the first one you should count positively, the second double intersections count negatively. And then the volume of the intersection, I guess you have to add sum over all of these j's. All right, that means sum over all different numbers of things you need to intersect. So I is the number of things that you need to, that appear in each of these intersections. -1 to the I plus 1, then add up all the different ways of computing these intersections. Yeah, oh, and I guess that was even going to go in that line. So let's just make sense of what that is. So that's just the content of this proposition 4 from last time's packet. Let's write down what this is when I equals 1. When I equals 1, we get, well, I guess that's -1 to the 2, which is 1, times the sum. So I equals 1, so it's, that only goes up to ji. So there's only one j1 to worry about, and that j1 index one of these jk, so it can go from 1 up to n of the volume of j sub j1. Hey, is that just the volume, the sum of the volume of the individual members of the subdivision? Yeah, who cares that the indexing variable is weird? So this is the same as the sum over j in delta of the volume big J, volume of j, which is exactly what we wanted. Let's look at any of the terms when I is bigger than 1. So in that case, we have -1 to the I plus 1, the sum over all choices of j1, j2, j3, up to ji of the volume of j1 intersect j2 intersect dot 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 intersect j sub j1 j sub j2 up to j sub ji. Oh, but wait, I mean, whatever this thing is, it's definitely contained in an intersection of at least 2 distinct elements of delta, right? Yeah, I want to add more detail than that. Well, j1 intersect dot 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 intersect j I is definitely contained in j1 intersect j2. But look at the definition of a subdivision. What's the volume of the intersection of 2 different elements of a subdivision? Zero? So the volume of j sub j1 intersect dot 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 intersect j sub ji is less than or equal to the volume of j sub j1 intersect j sub j2, which is equal to 0 as delta is a subdivision. So what is that sum equal to? 0. Yeah. So let's call this star. So that means that star is equal to 0. But that star was just like most of the terms in the sum that came from proposition 3 last time. So all of these sums, well, the one when I is equal to 1 is not necessarily 0. It's the sum of the volumes of the components. And then it's a plus a bunch of zeros. So what does this leave? So the volume of x is the sum over all j in delta of the volume of j minus 0 plus 0 minus 0 plus 0, and so on, which is exactly what we wanted. Cool, so that's nice anyway. That says that subdivisions are actually a reasonable way to subdivide a thing that you want to compute the volume of. And now you know how I'm going to define like these upper and lower sums. If I have let's go go back to this picture. If I have some little piece of the integral, I can estimate the volume over that piece on the one hand by drawing a little rectangle that just goes up to the smallest value you see on the graph of the function. And you can get an overestimate of the volume over that region by going up to the biggest thing you see on the actual graph. But we know how to compute the volume of each of those. It's just the area of the base times the height. So, and you can do that in any dimension. You just can't draw a picture beyond dimension 3, or at least I can't. So I'll define the lower Darboux sum. S of f corresponding to a subdivision delta is the sum of all of the little m of f comma j times the volume of j. S upper plus is the sum over all big M of f comma j times the volume of j, summing over all j in delta. Where little m is the infimum of the image of f over the set j, which hopefully is what I wrote.
Volume in R2 is just defined as area, right?
Yeah.
Okay.
Yeah. Yeah. Yeah, so because how do we define area, the drawn-on content on the area of a region? We broke it up into a bunch of honest two-dimensional rectangles and added up the areas of each of those. But the formula we gave for volume of an n-dimensional rectangle goes down to the definition of area. So you could do all this in one dimension too. You could figure out what a figure should be in one dimension, which would be something, it could be more complicated than just an interval. Not much. And then, right, you could write down the same thing. But the point is to have all the freedom. Where little m is the infimum and big M is the soup of the same thing. So far this is like the exact same definition as before. And I mean, all the things you know about integration and Darboux summation should still be true, right? So I guess one thing to note is if you want to define the integral, you need to take like better and better subdivisions. And what is a better subdivision? A better subdivision is a refinement of the subdivision you start with. And well, let's write down a definition of refinement then. Properties of If delta and delta prime are both subdivisions of x, then I'll say that delta prime is a refinement of x if, well, what do you think it should be? What was the definition in R1?
J in delta, there exists a subset of J in delta prime.
Almost, but flip the dependency. So you want to be able to say, well, if here is a subdivision in R1, then a refinement should like contain all of those breaks, but then also have some all. So each of these is contained in one of those. So that's the order. For everything in the refinement, there exists something in the origin. For all j prime in delta prime, there exists a j in delta such that j prime is a subset of delta prime.
Should we also have the union over all things in delta prime is equal to the original thing as well?
Yes, but that is built into this.
Oh, okay.
So in fact, there are a few things built into that. So I get, if you want to show that something is a refinement, you have to show it's also a subdivision. So, for example, here's a subdivision. Do you think from that you could draw an example of a refinement? Yeah, it would be like break it into all of those pieces, but now break each of those pieces up a little bit further. I mean, that makes reasonable sense, yeah? So, all of the properties that you know are true are still true. For instance, I think this summarizes like 3 different propositions that we prove about Darboux summation and refinements of subdivisions in our work. Let x be a figure, let f of x to r be bounded, let little m be the inf of f of x, big M be the sup of f of x, consider any subdivision delta of x and any refinement delta prime of delta. Then, m times the volume of x is less than or equal to an arbitrary Darboux sum, is less than or equal to the Darboux sum corresponding to a refinement, is less than or equal to the upper Darboux sum corresponding to the refinement, is less than or equal to the Darboux sum of the original subdivision, is less than or equal to the biggest thing that the volume could possibly be. That looks familiar, right? We proved that exact same thing if we were integrating over an interval already. And so maybe before we actually prove it, let's see. I'll number them. So the proof of item 1, which is the 2 extreme inequalities, is pretty short. The proof of item 2 is longer. About a page plus a little bit, though there are big gaps. All that is still 2. And then that middle inequality takes like half a line. So one of the reasons that I'm not sure how much time this lecture will take is I don't know how much detail you guys want to see. So you've seen that that's like 2 pages of argument that we can go through if you like. Is there demand? Okay. Maybe I'll point out that there is only one bit of subtlety. So because of the fact that I'm allowing for more complicated regions, means that some things which seem like they should be obvious are less obvious. For instance, let's look at that line right there. So, like, the primes are the things in the refinement, the ones without primes are the things in the original subdivision. So if you have an integration over R1, if you took all of the pieces of a subdivision contained in one of the, of a refinement contained in a single element of the original subdivision, you got set equality right there. The union of those 2 things is exactly that. That can fail now, because basically I'm allowing too many sets. But it doesn't make a difference. According to this, the volume of what you're off by is 0. And a volume 0 piece shouldn't be visible to integration anyway. So with that detail pointed out, do people now want to see the proof of item 2? Okay, let's do the proof of item 2. That's the only one that has really any difference. So let's get this declaration first. Let x be a figure, delta be a subdivision of x, let f be bounded. things we need. Let delta prime be a refinement of delta. So, by assumption, for any j prime and delta prime, there's some j in delta such that j prime is a subset of j. And there's like space here for a pause. I claim that the infimum of f of j should be less than or equal to the infimum of f of j prime. Why should that be?
Even over j prime is something that's contained j. The point that achieves the infimum is also in j.
There's no assumption of continuity. But, I mean, like, that idea should walk, right? So certainly f of j prime is contained in f of j. So that means that the infimum of f of j is a lower bound on f of j prime. That's true, right? But by definition, the infimum of f of j prime is the greatest lower bound. Inf of f of j prime is equal to the, well, this is just like, that's just another notation for it. The greatest lower bound of f of j prime, where there I've emphasized the g for greatest. Oh, yeah. So the classroom has moved since last semester. I can't see the screen even a little bit. So I know I do that a lot, and I know it's annoying, but maybe I should just wait until everyone leaves and push the whole room back when no one's looking. Okay, cool. So it's the greatest lower bound. This is the greatest lower bound. That's a lower bound. So inf of f of j prime must be greater than or equal to the inf of f of j. And notice we didn't need any assumption of continuity. We didn't need any assumption of anything about this function. I guess boundedness so that we could talk about infima. Otherwise the infimum would be minus infinity. People feel pretty okay about that? Nice. So now let's get to this bit which seems a little bit surprising. And first let's prove the thing that prove the subset containment, which seems like it should be equality. And in fact, this is like super obvious, I claim. And let's talk about why. And maybe I'll even just say the proof in words. How do you prove a thing is contained in another thing?
Take anything on the left, show that it's in the right.
Okay. So let's consider anything in this union. Since it's in the union, it has to be in one of those j primes. But what's true about each of the j primes that you take the union of?
It's in j.
Contained in j, so that thing must be in j.
So why does equality not hold?
Why does equality not hold? Let's draw a picture of why equality may not hold. Basically, I've allowed myself too much freedom in talking about figures. So there's a circle. I'll give a decomposition of it. So here's one of the pieces. Where that means that the blue bit doesn't contain that. And I guess the green bit can be and so let's think about just one piece of one of these subdivisions, what it could be. How about, well, it has to be contained in let's make another one of the pieces be that points. So suddenly the subdivision that I use doesn't need to have so if let's now just cut those out from these pieces, and there's the subdivision. Blue minus purple, green minus orange minus red, and then orange red. There's the subdivision. So let's see. This green bit, so let's try to find an element. So that's a point that's in the green thing. But notice that point isn't actually in the orange thing. It's in the purple thing. But the purple thing isn't a subset of the green thing. So the purple thing, I won't ever count in the green. So I might miss some bits of the boundary. If I've done that right.
Can you say that like in part again?
Yeah.
Oh.
I'm going to erase some of yours. Alright, so here's the subdivision I'll use. One of the pieces of the subdivision will be all of the green thing, except I won't include any of this boundary. And then, yeah, shoot, and then just use the blue thing as is. So there's a subdivision into two pieces. Is everything in the big set in one of the two new pieces? Yeah, because either it's in the blue piece, and so it's still in the blue piece, or it was in the green piece, and if it's in part of the green piece, it's not like this little piece, this little interval, then it's in the orange piece. If it wasn't this little interval, then it's in the blue piece. But notice that the only one of the new pieces that's contained in green entirely is the piece which I described as orange, which misses that little bit of green. But that little bit of green was volume 0 anyway, so it shouldn't matter. Let's just prove that it's always volume 0. And notice the reason kind of that you see that it can't be is the only stuff that you can miss must have been in another element of the subdivision. So anything in green that you missed must have been in green intersect blue. But what's the volume of the intersection of any two elements of the subdivision? So there's the idea of why. Let's explain why now. So here's the idea. Let's prove this by showing that J minus the union of all of the J primes in delta that are contained in J as subsets is contained in the intersection of all i's in the original subdivision delta, which are not equal to J, of I intersect J. So let's try to show that. And well, let's see. Let's let x be in J minus the union of all of these J primes. So then I see something already. X is definitely in J. So X is definitely in that J. Now I just need to show that it's in one of these i's other than J. Fair enough? Well, I know delta prime is a subdivision. So this is something contained in X. Now, delta prime is a subdivision. So, this X must be in some J prime. Maybe that's already indexing j prime. So x must be in some I prime in delta prime. Now, could that I prime possibly be a subset of j? No, why not?
Because x came from j minus the union of j primes.
Yeah, it couldn't possibly be in any of those. Delta is, I prime is not a subset of this particular j, but it must be contained in some I in delta, right? That's the definition of a refinement. But I prime is contained in I for some I in delta. Thus, x is in j, I intersect j for some I not equal to j, I in delta. Which is exactly what we need to conclude that set container, right? So that proves this. Nice. And, well, I guess I definitely haven't given myself enough space for that argument. But if this is contained in that, so the volume of j minus the union of j prime contained in j prime in delta, is contained in the union of all of these I intersect j's. So that means that you have an inequality of volumes. Oh, wait, but this is a union of a finite number of things, right? What's the volume of each element of this, each piece of this union? Zero. It's because they're both elements of a subdivision. So that's less than or equal to the sum of all these volumes of I intersect j's, but that's equal to 0. So the volume of that thing has to be 0. That seem pretty okay? And that's most of the subtlety. So why does that mean that the volume of j is the same as the sum of the volumes of the pieces? Well, the volume of j is equal to the volume of j minus the union j prime in delta prime, j prime subset equal to j of j prime union right, if you take j, you can write that as j minus some stuff, union some stuff. If you do back in exactly what you cut out. These two are now disjoint, so the volume should be additive. What's the volume of this piece? Zero. What's the volume of this piece? Well, it should be the sum of the volumes of the j primes, right? Nice. So, between these two ingredients, this fact and this fact, we have everything we need to prove that one of those middle inequalities. So m of f comma j times v of j, that should be the same as m of f comma j times the sum over all j prime in delta J prime contained in J, volume of J prime. And I could use delta prime. Yeah, thank you. I could distribute this m of f comma j into the sum. And m of f comma j is less than or equal to m of f comma j prime. So that's less than or equal to this. And you remember that was like a key part of the argument for intervals? Because now what am I going to do? I'm going to say, well, if I take this and I sum both sides over all deltas, then I'll see that the sum over all delta, j and delta, m of fj vj, is less than or equal to the sum over all j and delta of exactly that. But we already have a name for the thing that's on the left-hand side. What is this? That's like one of the Darboux sums, right? So that's s minus of f comma delta. On the right-hand side, well, that looks an awful lot like it might be one of the Darboux sums. Right, it's something like, if you take any, these are all the things that you would be adding up. And let's see if I even hit all of the j primes. Does each j prime show up at least once in this sum?
Yeah.
Because each j prime is contained in at least one of the j's. So that's good. Might this sum hit one of the j primes more than once?
Yeah.
Theoretically could happen. But let's think about which ones it does hit more than once. If it includes one of the j primes more than once, well then let's see, that means that j prime must be a subset of j, and j prime is a subset of some I for some I comma j in delta. But wait, what's the volume of the intersection of I and j then? What's the intersection of any two elements of, well, non-equal elements? So the volume of j prime is less than or equal to the volume of I intersect j, which is 0, as delta is a subdivision. So that means that I may as well just like throw all of those redundant zeros out of the sum. Right, some of the terms may have been counted like 5 or 6 times, but that's just 5 or 6 extra zeros. So I may as well throw those out and conclude that s minus of f comma delta oh, okay, well this is where the explanation for why the volume was supposed to be 0 was supposed to be. So the thing on the right-hand sum may as well just been the sum over all delta primes. I'm not done quite yet. I mean, I am maybe a minute over. So we'll pick this up next time. A lot of this is going to seem familiar from the like 2.5 days that I spent on figuring out how to integrate in R1. Just as you saw, things can get a little bit more complicated. But the bit that they'll get more complicated by is like volume 0. Cool. So let me point out the one thing that will actually seem new in this. It's that item 5 on page 7, which says that if you integrate over a union, well, that should be just like integrating over the sum of the two sums of the integrals, but you'll double count the integral over the intersection, which again shouldn't seem surprising. Does something seem wrong?
Should those be minuses in between the unions and intersections then?
Nope, because generally the intersection would be like over on that side being subtracted.